I'd like to discuss polynomial long division and some related ideas. There's a theorem, the division algorithm for z, and z is just a set of integers, and the theorem says given an a and an n, where a is contained in z, so a is just an integer, and n is contained in z, but n is greater than 0, so n is a positive integer, then I can take a and I can write it as a equal n times q plus r. And q and r are the quotient and remainder, and q and r are unique integers with r greater than or equal to 0 but smaller than n. I can take this equation over here and I can write it in fractional form by dividing by n, so I'll get a over n is equal to q plus r over n. And an example of that would be 3/5 with a equal 3 and n equal 5. And in this case, you can't divide the 5 into the 3, so you get a quotient of 0, and you get the 3 back again as the remainder. And if you have a fraction like this, where the numerator and the denominator are greater than 0, and the numerator is less than the denominator, that's called a proper fraction. If I take 3/5 and I flip it and get 5/3, then I can divide the 3 into the 5 and get a quotient of 1, and I get 2 left over, so I have a remainder of 2. And a fraction like this, where both numerator and denominator are greater than 0, but the numerator is greater than or equal to the denominator, is called an improper fraction. 5 over 5 would be another example of an improper fraction. 5 goes into itself one time, so you get a quotient of 1, and 5 goes into itself evenly, so you get a remainder of 0. There's an analogous theorem for polynomials, and that theorem is the division algorithm for the set of all polynomials with rational number coefficients. The q in this symbol over here stands for rational numbers, and a rational number is a ratio of two integers, like minus 3/5 would be rational because it's the ratio of two integers. 1/2 is the ratio of two integers, so that's rational. A whole number like 8 is rational because you can take a whole number and you can write it as itself divided by 1. So a whole number is also rational since it can also be written as the ratio of two integers. 8 is rational since it's equal to 8 over 1. And the theorem says that given an f and a g, where f and g are any two polynomials over q meaning with rational number coefficients, and g is not equal to 0, then you can take f and you can write f as equal to g times q plus r. And q and r are again quotient and remainder, and q and r are unique polynomials also over the rationals, and the degree of r is less than the degree of g. You can take this equation over here and you can write it in fractional form by dividing by g, so you'll get f over g is equal to q plus r over g. And it's also worth mentioning that the degree of a constant, if it's not equal to 0, is 0. So the degree of a non-zero constant is 0, and the degree of 0 is defined to be minus infinity. So if you have a polynomial like h equal 4, that's a polynomial of degree 0, and that can also be thought of as 4 times x to the 0. So, because anything to the 0 is equal to 1, as as long as that's something is not equal to 0. So the highest power of the variable that appears here is 0, so this is a 0th degree polynomial. And an example of this equation over here would be x squared over x cubed plus 1. Over here, the degree of the denominator is greater than the degree of the numerator. So you can't divide the denominator into the numerator. So you get a quotient of 0, and you get the numerator back again as the remainder. In general, the ratio of two polynomials is called a rational function. In a case like this, where the degree of f is less than the degree of g, the degree of the numerator is less than the degree of the denominator, like over here, that's called a proper rational function. Now, if I flip this, so I get x cubed plus 1 over x squared, I can divide the x squared into the x cubed and get x, and divide the x squared into the 1 and get 1 over x. Now if I take this expression here and compare it with this, I can see that x is equal to q, and the 1 over here is the remainder. And a fraction like this, where the degree of the numerator is greater than or equal to the degree of the denominator, is called an improper rational function. And here's another example of a proper fraction. The degree of the numerator is 0 and the degree of the denominator is 2. So in this case, the degree of the denominator is greater than the degree of the numerator, so I can't divide it into the numerator. So I get a quotient of 0, and I get the numerator back again as the remainder. Now, if I take this and flip it, I'd get an improper fraction. And what I can do here is I could take the numerator and I could factor 2 out of it. So I get 2 times 1/2 x squared plus x minus 2. Now the 2 in the denominator cancels with the 2 in the numerator, which means that the 2 divides evenly into the numerator. And if something divides evenly, that means there's a remainder of 0. And this stuff over here that's left over becomes the quotient. And this is also a polynomial over the rationals. In general, if you have a polynomial over the rationals and you divide it by a rational number, you'll get a remainder of 0, because you can always take a polynomial over the rationals and factor any rational you want out of it, since you could take any of the coefficients in the polynomial, and you could write that coefficient as any rational number you want times the coefficient over that rational number. This over here is the ratio of two rationals, which is also rational. So in general, a rational number will divide evenly into any polynomial over the rationals. This is another example of an improper fraction. Since the degree of the numerator is 1 and the degree of the denominator is 1, the degree of the numerator is equal to the degree of the denominator. So what I could do here is I could take the numerator and I could subtract and add 1 to it. So this plus this is equal to 0, so I don't change it. Then I could group these two together and have x minus 1, and add these two together and have plus 2. Then I could divide this into this and get a 1, and divide this into this and get a 2 over x minus 1. So over here I get a quotient of 1 and a remainder of 2. Over here I have an example of an improper fraction where I can factor the numerator. In this case, I can split the numerator into x minus 1 times x squared plus x plus 1. So the same factor appears over here and over here, so they cancel. So in this case, since they cancel, the denominator divides evenly into the numerator, and you get a remainder of 0. And this leftover part here becomes the quotient. So this is an example of g dividing evenly into f, so there's a remainder of 0. There's a particular corollary to the division algorithm for polynomials, and that's the remainder theorem. And you get that if you take this equation here and you let g equal to x minus c. So if you let g equal to x minus c, this equation becomes f of x is equal to x minus c times q of x plus r. And if I evaluate this equation at c, I'll get f of c is equal to c minus c, which is 0, so this term cancels, plus r. So I just get f of c is equal to r. And that tells me that if I have a rational function with a denominator of this form, I can evaluate the remainder just by evaluating the numerator at the value c. And you can also tell from looking at this equation that the remainder has to be constant, since the degree of the remainder is less than the degree of g, and the degree of g is just equal to 1. If the degree of r is less than 1, it's got to either be 0 or minus infinity, which means that r is a constant. And an example of the remainder theorem would be this fraction over here. And this fraction here is of the right form because I can take the denominator g and I can take the x plus 2 and I can write it as x minus minus 2. So this is of the same form as this, with c over here being equal to minus 2. So c is minus 2. So if I want the remainder here, all I have to do is evaluate f at the value minus 2. So f of minus 2 would give me 2 times minus 2 cubed plus minus 2 square minus 1. So that would give me 2 times minus 2 cubed, which is minus 8, which would give me minus 16, minus 2 square plus minus 2 square, which is 4 minus 1. So I'd have minus 16 plus 4, which is minus 12, minus 1, which is minus 13. So in this case, the remainder theorem tells me that the remainder is equal to minus 13, which means that I can take this fraction over here, the original fraction, and I can write that as q plus the remainder minus 13 over x plus 2. But this doesn't tell me what q is. So suppose I wanted both q and r. Well, in that case, you could use the polynomial long division algorithm. And this is a general algorithm and works for any two polynomials as long as g is not equal to 0. So if I apply it to this fraction that was just considered, what I would do is write this fraction out as a long division problem. You take the numerator, 2x cubed plus x squared minus 1, and write it here. The numerator here is missing the first degree term, so I'll just put a 0 in as a placeholder for that term, take the denominator and put it over here. So what you do now is you take the first term in the denominator and you divide it into the first term in the numerator. So you'll have 2x cubed divided by x, which is just 2x squared. So what I'm doing, 2x squared. So what I'm doing is I'm taking the first term in the numerator, 2x cubed, and I'm dividing that by x, and that gives me the first term of the quotient, 2x squared. Then, after you do that, what you do is you take the term in the quotient and you multiply that by each term in the denominator. So 2x squared times x will give me 2x cubed. So I got the 2x squared by taking this term, the 2x cubed, and dividing it by this term. So this term over this term gives me this term. So when I multiply this term in the quotient times this term again, it's the same as multiplying this times this, which gives me the 2x cubed, which is the first term of the numerator, back again. And then I multiply this times the 2, and that gives me 4x squared. Just fix that. So now what I do is I subtract this. I subtract this from the numerator, and subtracting one number from another number, like a minus b, is the same thing as adding minus that number. So a minus b is the same thing as a plus minus b. So what I do here is I take the 2x cubed and multiply it by a minus sign, and that gives me minus 2x cubed. And when I add it to that, they cancel. And then I take the 4x squared and multiply that by a minus sign, and get minus 4x squared. Add it to that, gives me minus 3x squared. And then I'll bring down the remaining two terms in the numerator. And then after you complete that, you get this modified numerator over here. And then when you get that modified numerator, you repeat the process again. So now that I have the modified numerator, I repeat the process and divide the first term in this modified numerator by the first term in the denominator. And that's 3x squared divided by x, which is 3x. And then I get the newly generated term in the quotient. Which is just 3x. And then I take that newly generated term in the quotient and I multiply it back times each term in the denominator. So then I have minus 3x times x, which gives me the minus 3x squared back again. So I got this term by dividing this term by this term. When I repeated the process, I divided this term by this term again, and that gave me the next term in the quotient, minus 3x. So when I get to this step where I multiply this back by the x, that's the same as minus 3x squared times x, which gives me the minus 3x squared back again. So I get this term back again. And then I multiply the minus 3x times the 2, which gives me minus 6x. And then I have to subtract this term from this modified numerator. So I put a minus sign over here. So minus 3x squared times a minus sign is plus 3x squared. And when I add it to that, they cancel. Minus 6x times a minus sign is plus 6x. And I add that to the 0 and I get the plus 6x again. So every time you repeat this step, the first terms should cancel. Like over here and over here. If they don't cancel, it means you've made some mistake. And I still have this minus 1 left in the numerator, so I'll bring down that term. And then you get the new modified numerator. So you repeat the process again and divide the first term in the denominator into the first term in this modified numerator. And that would be 6x divided by x, which is just 6. Now that you've gotten the new term in the quotient, you have to multiply it back by each term in the denominator again. So you'll have 6 times x, which will give you the 6x back again. And you'll have 6 times plus 2, which will give you plus 12. So you have to subtract that now from this modified numerator. So you'll have 6x times a minus sign is minus 6x added to this 6x, and they cancel. And you'll have 12 times a minus sign, which is minus 12, added to the minus 1 is minus 13. So the minus 13 would be the next modified numerator. Now, if I try to divide the first term in the denominator into the minus 13, I can't do it because this is of lower degree than this. So that's where the process ends. And the minus 13 becomes the remainder, and all this stuff over here becomes the quotient. So if you look at this again, you'll see that every time you get a modified numerator, it's of lower degree. This is third degree, this one here is second degree, the next one is first degree, and this last one is 0th degree. So when the degree of the modified numerator is less than the degree of the denominator over here, that's when the process stops. So I can take the original fraction over here and I can write it as the quotient, 2x squared minus 3x plus 6 plus the remainder minus 13 over x plus 2. And we get the same remainder as we did when we used the remainder theorem, as we should. This was a special example with a denominator of first degree and a coefficient of 1. But this is a general algorithm, and it'll work on any two polynomials as long as the denominator is not equal to 0. So here's an example with a denominator of degree 3 and a numerator of degree 4. You take it and you write it as a long division problem. The numerator, you have x to the 4th, but the numerator is missing 3 terms, so I'll put a 0 there to mark the cube term, and a 0 here for the square term, and a 0 here for the first degree term. Put the 1 here, take the denominator, put it here. And now you divide the first term in the numerator by the first term in the denominator again, so you have x to the 4th divided by x cubed, and that just gives x for the first term of the quotient. And then when you get the new term in the quotient, you just multiply it back out times each term in the denominator. So x times x cubed gives me x to the 4th again. X times x gives me x squared. And x times 2 gives me 2x. So I take this and I subtract this from the numerator. X to the 4th times a minus sign added to this is 0, so these two terms cancel. X, oh, this is supposed to be x squared. This times this was x to the 4th, this times this should be x squared, and this times this is 2x. So x squared times a minus sign is minus x squared, added to the 0 gives minus x squared back again. And 2x times a minus sign is minus 2x, added to this gives me minus 2x back again. And I'll bring down the remaining term in the numerator, the plus 1. Now, at this point, I can't divide this term here into this term here, because this term here is of lower degree. So the process stops over here, and the quotient is just x, and the remainder is minus x squared minus 2 plus 1. So the process continues till you get a modified numerator of lower degree than the denominator. So the process stops here, because this is second degree and this is third degree. So now the original fraction over here can be written as the quotient x plus the remainder minus x squared minus 2x plus 1 divided by the denominator x cubed plus x plus 2. And I'm just going to end on an interesting side point. Suppose I were to take the division algorithm for z, and suppose I let a equal 5 and n equal 7. So a over n becomes 5 over 7. I can't divide the 7 into the 5, so I get a quotient of 0, and I get 5 back as the remainder. I can also consider the 5 and the 7 as polynomials, so I can let f equal 5 and g equal 7, and then I can take the division algorithm for polynomials, and I get f over g being equal to 5 over 7 again. And I can factor the 5 into 7 times 5 over 7. So the same factor appears here and over here, so these two factors cancel, which means that the denominator divided evenly into the numerator. So I get a remainder of 0. And this stuff left over here, the 5/7, becomes the quotient. So when I took 5/7 as a ratio of integers, I get a quotient of 0 and a non-zero remainder. When I take 5/7 as the ratio of two polynomials, I get a non-zero quotient and a 0 remainder.